Hey guys, welcome again to our YouTube page. So our YouTube channel. Today we are going to look at an exciting topic. We are going to look at understanding regression analysis. So we are going to go from the basics to the complicated stuff. So we shall be following this book. I made for you this book which explains basic principles of regression. So we shall be moving along with this book. So if you want to support me, I'll leave a link where you can get this book. It costs only $5, and you follow through. Thank you. Today we are going to look at straight line regression analysis, and it's going to be linear regression. Specifically in this video, I'm going to take you through the theory of linear regression and when do we use a linear regression and how do we test the assumptions of a linear regression. So by definition, we see that regression analysis and statistical processes or methods that are used to estimate and describe relationships between an independent variable or an outcome with one or more independent variables. So we want to determine a linear relationship between one outcome versus one or more independent variables. For example, this applies in so many areas of research or in daily things. So let's look at an example which is a basic example. So let's look at an example of a broker determining or predicting prices of houses in a geographical area A using the features of size, location, number of bedroom, price, land, and price of land in the area. So he gets the prices and features of houses in area B and uses this data to determine or predict the prices of houses in area A. So this is the data of the prices of houses in area B. So he gets this data and uses this data to determine or to predict what would be maybe the price of a house which is located in a rural area with 5 bedrooms and land this size. So looking at your own eyes, what we call eyeballing, you can't really predict the price of a house, for example, with a 2,000 square meter size located in a rural area with 6 bedrooms and land. The price of area is 4,000 USD per square feet. You cannot. So, but we can use what we call linear regression, such that we fit these points on the y points, we fit them alongside these values, and we draw a line of best fit which we can use to determine the prices. So what are the mathematical properties of a linear regression or a straight line model? So the expectation of y on x is equal to beta naught, which is called the y-intercept, plus beta 1 x. So beta 1 is the slope and x is the independent variable. All y small y is equal to beta naught plus beta 1x plus e is the error term. So the error we get while estimating the values of y on x, which is normal. So what do we mean that by the intercept? Y-intercept is the value where the slope meets the y-axis. So we see for y1 it has a negative slope since the curve is the straight line is going down, and y2 has an intercept of -4 and it is a positive slope or a positive beta 1. So from this figure 1.1, we can see that y1 has a y-intercept of 5 and y2 has a y-intercept of -4. The slope is negative or positive by determining the direction. So I have already explained that. So now let's go ahead and consider a sample of houses versus the size of geographical area in this table. So if we are to determine, we have this data and we want to determine maybe if we want to predict the price of house with a size of 18 square foot. So you are given these data points and they tell you what would be the size of a house with 18 square foot. So you can't just eyeball and say maybe it should be below this and it is maybe 180,000 US dollars. No, we need to first fit the values of y on x onto the graph and determine the line of best fit, which gives the least error estimation. This is very important. So we can now predict the price of the house with a size of 18 square feet from the equation. So if we look at this line, let's first erase this. We don't need them. Okay. So if we look at this equation here, we have scattered the plot of y on x. It's price versus size, and we fit a line with the minimal error estimation of the exact value, which is from the points on the y-axis. So it gives this equation. It gives the equation of y is equal to 47.506 per 10.139x. So this is the y-intercept, and this is the beta 1, or the slope. So if we want to get the price of the house with 18 square foot, you just feed in the value of x, which is 18, and you get $230,000. You see, if you just used your eyes, you would say maybe it is 180,000, but you see it's 230. So what are the statistical assumptions for a straight line regression model? When do we really use a regression analysis? Because we don't just pick a regression model and we use it. We have to first know all the assumptions are fulfilled and we use it. For a linear regression model, it has its own assumptions. First of all, the first condition, the outcome has to be should be continuous variable. Yeah, if it's not, or if it's categorical, or a count, or something else, we use different regression methods. It has to be a continuous variable in the first place, the outcome. So suppose we want to determine the relationship between a house price y and size. We need to determine the line of best fitting our data. If all points on a scatter plot of y and x were a straight line, we would simply draw a line touching all points. That would be our line of best fit. Unfortunately, that's not how things work in real life. So if the prices of houses versus the size, they were predicting perfectly, all these blue dots will be fitting on this straight line. But that's not how it works. So we have to estimate where can this line best fit these points with the minimal error of estimation. So that's where we go to what we call assumptions. So this means that our true line of best fit will approximate a distance with minimal error for each point on the scatter plot that can be used to determine the relationship between y and x. Since this data is from one area or the sample population, we need to make assumptions to enable us make inferences to our target population. So we know that the target population is that larger population where you want to infer your data to. Accessible population is that population that you can access when you want to collect to do a study, and the study population is that sample that you get from an accessible population. For example, if you are in the United States and you want to infer data to a whole state, for example Connecticut, you need to sample out. Maybe you can access only participants from all houses in New Haven. So you sample out houses in New Haven, but you want to study the entire New Haven. So maybe you want to study one of our line street, maybe Elm Street, and you want to determine the prices of the houses of LM Street, and that is your study population, that's your sample. So that's the meaning of this target and accessible and study population. So what are the assumptions? To determine the assumption of straight line regression, we shall consider an example with more than one predictor, i.e. multiple regression. So this we shall use the data from this link. So you'll find this link into this PDF file. I will put the link in the description. So the first assumption of linear regression is existence. So, but before we go to that, let's look at our data. Let's first browse and look at our data. So this is the ID of the patient ID, the age, sex, height, weight, FEV, which is called forced expiratory volume. It is used to determine the pulmonary function. How well are your lungs functioning? So you blow up air into a machine that measures this value. So that's how these patients were taught to blow air into this machine and gave this value. So we have body group and BMI. We calculate BMI from height and weight. BMI equals weight over height in meters squared. So we want to predict what is the lung function of patients while using their age, sex, blood group, and BMI. So this is the data set we are using. So by just summarizing our outcome, FEV, the forced expiratory volume. So we see that we have 60 observations. The mean is 3.7, standard deviation is 0.87. The minimum value is 2 and maximum value is 5.2. You can just describe and we see the entire data set because there are a few variables. Body group is a byte, FEV is a double, sex is a byte. So we can just see how we have 60 observations and 8 variables. That's what the describe mean. If we want to see if our outcome is normally distributed, we can just do a histogram and we put a normal distribution curve. Wow, it's an absolute disaster. It's not normally distributed at all. So, but we don't care about that because that's not the case. We shall see. So first of all, the first assumption, and this is the biggest or the most important assumption, is existence. So for existence, for any fixed value of x, y is a random variable with a certain probability distribution with the mean of y of x and variance sigma. So first of all, we want to establish a relationship between the dependent variable and the independent variable. Does that relationship is that relationship there? So let's first establish the relationship by using something simple like a correlation coefficient. So if the pairwise correlation coefficient is greater than 0.3, then we shall see at least there is some relationship that exists. So if it doesn't exist, we don't even continue because we can't determine we can't start to regress things that don't have any relationship connecting them. So if we determine the pairwise connection, we can see that age is negatively correlated to FEV, BMI is only 17% correlated, BMI and age is correlated negatively 0.154. So at least there is existence is fulfilled. There is some correlation there. There's some connection there between for the variables y and x. So let's go ahead and test the assumption of linearity. So this linearity assumption, it means that the mean value of y on x is a straight line function of x. This means that if we connect the mean values of y on x, we get a straight line. So if we scatter these mean plots, we must get a straight line. So for that, we shall test this assumption using the component plus residual plots, or the CPR plots. So we first run our regression line, then we plot the CPR plots using a lowest smoother. A lowest smoother helps us to determine the trend line. So let's go ahead and okay, this is not the one. Okay, all right. Let's go ahead and run our regression line. So the regression is, you just type regress. This is a linear regression, multiple linear regression. Regress FEV, the outcome, with the independent variables. For categorical variables, you can use I dot to show the dummy variables, and we shall use BMI. We shall use BMI, age group, and sex and age as our independent variables. So we get the residuals. We shall know how to explain this regression model, but today we are concentrating first on the assumptions. If the assumptions hold, then we go ahead and we run a regression model and we explain it and so on and so forth. But let's first determine the assumptions. So the assumptions that we are testing right now is we are going to plot a CPR plot. We first predict the residuals. So by predicting the residuals, because we are plotting, so we predict the residuals, then we also predict y hat. Y hat is the estimated values of y in a regression line. So we predict y hat and the residuals. So the CPR plot uses those to determine how. Okay, this is how now. This is a plot of a CPR plot of age in a regression line. This straight line going down is the line of best fit, and this curved thing is the lowest smoother. So the lowest smoother is supposed to give us a trend, but you see here that it's in a straight line. In the straight line regression analysis, it is supposed to be a straight line, but here we see that it's moving up and down and things like that. So that means this doesn't hold. This assumption is violated. So let's do a CPR plot for BMI. We do this for continuous variables. So you see, at least for BMI it holds. You see, at least it is a straight line. It is assuming the smoother is assuming a straight line. Yeah, it doesn't have to be completely straight, but at least it's a straight line. This assumption now holds for BMI, but doesn't hold for age. So since it doesn't hold for age, we are going to introduce a higher order term in order to correct this. So a higher order term we want to introduce is first of all, it can be a natural log, it can be age square, cubed. So let's first deal with the age square. So we generate age square equals age times age. So age times age, we generate an age square, then we run our regression again. By the way, if you're running a regression line with a higher order term, also the variable which gave us the higher order term has to be in the regression model. So we plot our CPR plot with the lowest smoother. You see that when we introduce a higher order term, it gave us a straight line. So the smoother shows a straight line trend. So you see that now edge has to work with a higher order term, with its higher order term. Without it, nope, things won't work. So that means edge violates the assumption of linearity. But if we include the higher order term, edge gives up and gives us a straight line and a smoother. So let's look at a third assumption called independence. So this assumption, the y values are statistically independent from each other. So the outcomes are independent from each other. This means that each value of y, for example, in this example we have used FEV, was collected on a different individual. So there should not be any correlation within y variable. This assumption, if this assumption is violated, this assumption is violated in repeated measures of the outcome. So for this case, we use ANOVA or GEE as a regression. So how do we, when does this assumption get violated? For example, if we are determining weight of students over time, maybe weight when they have just joined the school, then weight after they finish first year, second year, and third year. So we are determining weight from the same individuals. So when you enter, we take your weight. When you leave in first year, we take your weight. When you leave in second year, we take your weight. And when you leave in third year, you see that the weight, the third or second or the fourth weight, depends on the first weight you had, or the third weight depends on the second weight you had. That means the outcome is correlated. You have a correlation. So for that, we don't use a linear regression. Although it is a continuous outcome, we don't use a linear regression because the assumption of independence is violated. The y values are not independent from each other. To determine this assumption, we just plot RV plots. Let's see. So by plotting RV plots of BMI and edge square, so you see that it should give you a straight line through zero with these points scattered around this line with no pattern. So that shows they are not correlated. They are not correlated. These are values of the y. So then let's do this for edge. Still no correlation in the y. So for this assumption of existence is fulfilled with RV plots. They show no pattern. It means independence assumption is fulfilled. So let's go ahead to the fourth assumption, which we call homoscedasticity. Homoscedasticity comes from two words, homo, same, and scedastic, scattered. So the variance of y is the same for any value of x. That's what it means. One method of testing this assumption involves the post-estimation test for heteroscedasticity. Hetero is the opposite of homo. So if the null hypothesis, this test for heteroscedasticity has a null hypothesis of variances are equal. By giving us a non-significant p-value, we hence fail to reject the null hypothesis and conclude that there is equal variance. So let's do that and we see. So just a simple test of heteroscedasticity. These commands are within the PDF. So we see that the p-value is not statistically significant. So that means it holds. So let's go ahead and look at the assumption of normality. So normality is normality or normally distributed residuals. Remember, it is normality or normal distribution of residuals. So for any fixed value of x, y is normally distributed. This assumption is tested by plotting the k-density plot, histogram, the p-norm or the QQ plots. We shall see. So they should give you this pattern, which shows a very beautiful normal distribution. The p-norm and the QQ plot, they should give you points that are in a straight line. So let's go ahead and test this assumption. So we do the histogram of residuals. We already predicted our residuals. You see, oh wait, these are the residuals that we predicted without the higher order term. So we have to first drop these residuals and predict the different residuals when we included the higher order term. So we can predict the residuals and the y hat. So if we go ahead and do a histogram, you see now that it's different. It's a very beautiful histogram which shows a normal distribution. So we go ahead and we test, we do a k-density plot. So the k-density plot and the histogram, they're almost the same. So yeah, it shows a very good normal distribution. So the k-density is the one which is on in the below, and the normal density is the one in the right. They show a very good, beautiful normal distribution. So we can go ahead and we do the p-norm and the q-norm. You see they are on a straight line. So we can do also the q-norm, or what we call the QQ plots. It's also on the straight line. That means the assumption is fulfilled. So the next assumption is collinearity. So this is very important, by the way. Here we test the correlation between independent or predictor variables, so such that they express a linear relationship in the regression model. These cannot, if there is any relationship or correlation between the independent variables, they cannot independently predict y. Therefore, one of them is removed. For example, let me give you an example. We determine BMI from height and weight. So we can't have a model which has height, weight, and again BMI. Since they come from the same, that means they are very connected. They are not independent. They are so strongly correlated. They are so connected. So they cannot independently predict the outcome. So we have to remove the weight and the height and remain with BMI. So you can find that some independent variables you corrected, they are so connected to each other and they cannot independently predict the outcome. So we remove them. So for this case, I'll give you an example and show you. Let's run our regression model. And then estimate the variance inflation factor. We test this assumption using the variance inflation factor, or VIF, and 1 over VIF. If 1 over VIF is less than 0.1, or if VIF is greater than 10, it means there is correlation. You see that edge square was gotten from edge, that's why VIF is greater than 10. It means these ones cannot independent